Right now, as you are watching this, power grid operators across North America, Europe, Asia, and Australia are running contingency protocols. They have not activated simultaneously since 2003. NOAA's Space Weather Prediction Center in Boulder, Colorado, issued a G5 geomagnetic storm warning at 11:42 UTC on July 26, 2026, the highest category on the geomagnetic disturbance scale. The European Space Agency activated its space weather service network within the same hour. Japan's National Institute of Information and Communications Technology issued a nationwide radio disruption alert, and Australia's Bureau of Meteorology Space Weather Services put every critical infrastructure operator on the continent on formal notice. 4 continents, 1 source, and the source is 150 million kilometers away. On July 24, 2026, sunspot region AR 4821. A magnetic structure on the surface of the Sun, roughly 14 times the diameter of Earth, released an X94 class solar flare, the most powerful category of solar eruption, at 8:17 UTC. That flare ejected a coronal mass ejection, a billion-ton cloud of magnetized solar plasma, directly toward Earth at an estimated speed of 2.4 million kilometers per hour. At that velocity, the CME covered the 150 million kilometer distance. Between the Sun and Earth in approximately 38 hours, it arrived on the night of July 25th and immediately began compressing Earth's magnetosphere, the magnetic field that surrounds and protects the planet, driving it to conditions that triggered the G5 classification within 6 hours of first contact. The last time Earth experienced a G5 geomagnetic storm was May 2024. Before that, it was the Halloween storms of October 2003. We are now in the peak of solar cycle 25, the current 11-year cycle of solar activity. And scientists at NOAA's Space Weather Prediction Center have confirmed that this cycle has produced more X-class flares than any cycle since solar cycle 19 in the late 1950s. AR 4821 is the most magnetically complex sunspot region to emerge on the solar disk in that entire period. Today we are going to break down exactly what a G5 geomagnetic storm does to the systems modern civilization depends on, what happened the last time the Sun produced an event of this scale, and why it matters that it happened in 1859, and whether what scientists are measuring from AR 4821 right now suggests the worst of this storm cycle is already behind us, or still ahead. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Did you see the aurora last night? A G5 geomagnetic storm pushes the visible aurora borealis as far south as Florida, Texas, and northern Mexico in North America, and as far north as New Zealand in the southern hemisphere. If you saw it, tell me your city and what color it was. Thousands of people watching this channel are seeing the aurora for the first time in their lives right now because of what AR 4821 just did. I want to hear where you are and what it looks like. If you want to be the first to know, every time NOAA's Space Weather Prediction Center issues a significant geomagnetic storm update, subscribe right now. It is completely free. A thumbs up helps this reach people who need to understand what is happening to their GPS, their radio, and potentially their power grid right now. Let us go for 5,000 likes on this one. Now, let us talk about what a G5 storm actually does. The geomagnetic storm scale runs from G1 to G5. G1 is minor, weak power grid fluctuations, aurora visible at high latitudes, minor satellite orientation effects. G5 is extreme, the highest classification, and what? Tact it produces at the infrastructure level is qualitatively different from anything below it. Here is the mechanism. When a coronal mass ejection arrives at Earth, it carries its own magnetic field embedded in the plasma. If that embedded magnetic field is oriented southward, anti-parallel to Earth's own northward-pointing magnetic field. The two fields connect and merge in a process called magnetic reconnection. Energy from the solar wind pours into Earth's magnetosphere through this connection and drives intense electrical currents in the upper atmosphere, in the ionosphere, and critically along the surface of the Earth itself. Those surface currents are called geomagnetically induced currents, or GICs. They flow through anything conductive at ground level. That includes power transmission lines, pipelines, railway tracks, and the transformers that sit at the nodes of every major power grid on Earth. Transformers are the specific vulnerability that makes geomagnetic storms a serious infrastructure threat. A large, high-voltage transformer, the kind that steps power up to transmission voltage and back down for distribution, is designed to handle alternating current at 50 or 60 cycles per second, depending on the country. The quasi-direct current induced by a geomagnetic storm flows through the transformer's core at effectively 0 cycles per second. Second, this DC bias saturates the transformer's magnetic core, causing it to draw enormously increased reactive power, generate intense internal heat, and in severe cases, fail permanently. The word permanently matters. A large high-voltage transformer is not a component that can be replaced quickly. There are approximately 2,000 large power transformers in the United States grid. Most are custom-built, individually engineered for specific locations, and manufactured in a supply chain that produces approximately 70 to 100 units per year globally. The lead time from order to delivery is between 12 and 18 months under normal circumstances. If a severe geomagnetic storm damages or destroys dozens of these transformers simultaneously across multiple grid regions, the replacement timeline is not days or weeks, it is years. As of the time this video was produced, grid operators in the northeastern United States, Canada, the United Kingdom, and Scandinavia, the regions at highest geomagnetic latitude and therefore highest GIC exposure, had implemented protective switching protocols designed to reduce transformer vulnerability during the storm's peak. These protocols involve deliberately reducing power flow through the most exposed sections of the grid, accepting localized service reductions to protect the transformers that cannot be replaced quickly. This is the difference between a storm that causes temporary disruptions and a storm that causes permanent infrastructure damage. The current G5 event has produced GPS accuracy degradation of 20 to 50 meters across large portions of North America and Europe. High-frequency radio communications used by aviation, maritime, and emergency services have experienced significant blackouts across the sunlit side of the planet. Satellite operators have reported increased orbital decay rates requiring corrective maneuvers. An aurora has been visible as far south as latitude 25 degrees north, Mainz, covering Florida, the Texas Gulf Coast, the Canary Islands, and northern India. None of this is unprecedented, but the combination of intensity and duration of this event places it firmly in the category of storms that stress test modern infrastructure in ways that normal operations never do. Now let us talk about what happened the last time the sun produced a storm that makes the current G5 look manageable. Because the Carrington event of September 1859 is the reference point that every space weather scientist returns to when they are asked what the true upper boundary of solar threat looks like and what it would mean if it happened today. On September 1st, 1859, British astronomer Richard Carrington was observing a large sunspot group through his telescope when he witnessed something no human had ever recorded seeing before. A sudden, intense brightening on the sun's surface that lasted approximately 5 minutes. What he had observed was a white light solar flare, the most powerful class of solar eruption. 17 hours later, the fastest transit time ever recorded for a CME, the Associated Plasma Cloud, arrived at Earth. The geomagnetic storm that followed was of a scale that has no equivalent in the instrumental record. Modern scientists, reconstructing the event from magnetometer records preserved at observatories in Bombay, Greenwich, and Colombia, have estimated the storm's peak intensity as roughly twice the strength of the strongest storm measured in the modern satellite era. Telegraph systems across North America and Europe simultaneously failed, caught fire, or began operating without battery power from the electrical currents the storm induced in their lines. Telegraph operators received electric shocks from their equipment. The aurora was visible in Honolulu, Cuba, and Colombia regions where aurora is essentially never observed under any normal conditions. The Carrington event was a catastrophe for the most advanced communications technology of 1859. The telegraph network of 1859 and the power grid of 2026 share a critical structural characteristic. They are both large conductive systems that span continental distances and are therefore maximally exposed to geomagnetically induced currents. The difference is that the telegraph network of 1859 was not civilization critical infrastructure in the way that the modern power grid is. Losing telegraphs in 1859 was a serious disruption. Losing significant portions of the modern power grid would be a civilizational scale crisis. Lloyd's of London, in a 2013 assessment of Carrington-scale geomagnetic storm risk, estimated that a direct repeat of the 1859 event, striking the modern United States, would produce between $0.6 and $2.6 trillion in economic damage, with between 20 and 40 million people losing power for periods ranging from 16 days to 2 years, depending on transformer damage extent. The FEMA and Department of Homeland Security assessments are the same. The scenario have consistently placed it in the category of events that would overwhelm the standard disaster response framework designed for localized, catastrophic events. Now here's what the contrast tells us about where humanity currently stands relative to that risk. In March 1989, a G5 geomagnetic storm struck Earth during a period when grid operators had essentially no protective protocols in place for geomagnetic disturbances. Hydro-Quebec, the electrical utility serving the Canadian province of the Quebec, experienced cascading grid failure within 90 seconds of the storm's peak ground current surge. 6 million people lost power. The outage lasted 9 hours. 7 large static VAR compensators, devices that help stabilize grid voltage, were permanently damaged. The total direct cost to Hydro-Quebec alone was estimated at 2 billion Canadian dollars in 1989 values. The response to 1989 was not nothing. North American grid operators subsequently developed the first generation of geomagnetic storm operational protocols. Monitoring systems were enhanced. NERC, the North American Electric Reliability Corporation, issued guidelines for geomagnetic disturbance preparedness that have been progressively strengthened across the decades since. When the G5 storm of May 2024 arrived, the strongest storm since the 2003 Halloween events, the northeastern U.S. and Canadian grids implemented protective switching within the warning window provided by NOAA's Space Weather Prediction Center, and no major grid failures occurred. The current July 2026 G5 event is unfolding against that improved but still incomplete preparedness backdrop. Grid operators have more tools, better warning systems, and clearer protocols than they did in 1989. What they do not have is a guarantee that those tools are sufficient for a Carrington-scale event, because no Carrington-scale event has tested them. When you lay all of this out, AR4E21 X94 flare, the G5 storm hitting 4 continents simultaneously, the GPS degradation, the radio blackouts, the protective switching protocols running across the northeastern grid, the natural question is whether this represents something outside the normal range of solar activity. The honest scientific answer is no. The sun has been producing cycles of maximum and minimum activity for billions of years. Solar cycle 25 is more active than scientists predicted at its outset. NOAA's Solar Cycle 25 prediction panel initially forecast a modest cycle and has revised that prediction upward 3 times since 2020, as the cycle has consistently outperformed expectations, but the existence of active solar cycles is not anomalous. The activity we are seeing from AR4821 is at the high end of what Solar Cycle 25 has produced, but not outside the bounds of what previous cycles have produced in the satellite era. What has changed is what is at stake. In 1989, when the G5 storm blacked out Quebec, the internet as a global infrastructure did not exist. GPS was a military system with limited civilian deployment. Satellite-dependent communication was minimal. The modern economy's dependence on GPS for financial transaction timing, for aviation and maritime navigation, for logistics routing, for agricultural precision equipment, creates a vulnerability to geomagnetic disruption that did not exist in 1989 and did not exist at all in 1859. Let us be direct about the practical message here, because information without action is just anxiety. NOAA's Space Weather Prediction Center provides real-time geomagnetic storm alerts that are publicly accessible. Add NOAA's space weather to your notification sources. During a G3 or higher geomagnetic storm, GPS accuracy degrades. If you depend on GPS navigation for critical operations, commercial aviation, maritime navigation, precision agriculture, emergency services dispatch, understand that accuracy may be degraded by tens of meters, and plan accordingly. Keep a battery-powered or hand-crank emergency radio. In a scenario where grid disruption affects your area, cellular towers have backup power that lasts between 4 and 8 hours in most markets. After that, battery-powered radio is your primary information source. This applies in any grid disruption scenario, not only geomagnetic storms. Keep 72 hours of cash available. ATMs and card payment systems depend on network connectivity and power. In any extended grid disruption, cash becomes the functional medium of exchange for the duration. If you live at a high geomagnetic latitude, minus Canada, Scandinavia, the northern United States, Scotland, New Zealand South Island, and the aurora you may be seeing right now is not a threat. It is the visible byproduct of the same storm that is stressing the grid. Go outside and watch it. It is one of the most extraordinary things the natural world produces. Just understand that what is making it visible is also running induced currents through the power lines above your head. Final thought. The sun has been doing this for 4.6 billion years. Solar maxima have come and gone. CMEs have struck Earth's magnetosphere, and geomagnetic storms have compressed and disrupted the planetary magnetic field across the entirety of Earth's history. The difference between the Carrington event in 1859 and the Carrington scale event today is not the sum. It is what humanity has built in the 167 years since, and how much of it turns out to be invisibly dependent on the assumption that the sun will remain quiet. We cannot stop a coronal mass ejection from leaving the sun. We cannot deflect it. We have approximately 15 to 45 minutes of warning between the CME's detection at the L1 monitoring point and its arrival at Earth, barely enough for grid operators to implement protective switching and satellite operators to put assets in safe mode. What we can do, what the difference between Quebec 1989 and May 2024 demonstrates is genuinely achievable, is build the monitoring systems, the grid protocols, and the operational culture to minimize what a major geomagnetic storm does when it arrives. The 1989 event changed grid protocols. The 2003 events changed satellite operations. Every major storm since has refined what the preparedness framework looks like. The Carrington event has not repeated. When it does, the question of whether civilization's response looks more like Quebec 1989 or May 2024 will depend on decisions being made right now in grid control rooms, in satellite operations centers, and in the government agencies responsible for space weather preparedness. We will track every NOAA Space Weather Bulletin and every significant development from AR 4821 as this storm continues. Subscribe so you do not miss it, and leave that comment below. Did you see the aurora? Tell me your city, because the same event that is running induced currents through the northeastern power grid right now is also painting the night sky in colors that most people on this planet will never see in their lifetimes. And that is worth a moment before we get back to worrying about the grid. 5,000 likes? Let us go. Sources: NOAA Space Weather Prediction Center, G5, Geomagnetic Storm Warning and Advisory Bulletins, July 26, 2026. NOAA Solar Cycle 25 Prediction Panel Revised Forecasts, 2020-2026. European Space Agency Space Weather Service Network, Activation Bulletin, July 2026. Japan National Institute of Information and Communications Technology, Radio Disruption Advisory, July 2026. Australia Bureau of Meteorology Space Weather Services Critical Infrastructure Bulletin, July 2026. NERSI Geomagnetic Disturbance Operational Guidelines and 2024 Compliance Assessment. Lloyd's of London, Solar Storm Risk to the North American Electric Grid Assessment, 2013. FEMA and Department of Homeland Security Electromagnetic Event Preparedness Assessments. Richard Carrington, Original Observational Records, September 1859. Cliver and Svalgard 2004, Reconstruction of Carrington. Event, Geomagnetic Intensity in Journal of Geophysical Research. Hydro-Quebec, March 1989 Storm Impact Documentation. NOAA, SWPC, May 2024, G5 Storm After Action Review.